Hi, today we are introducing direct current circuits. We start with series and parallel configurations. Resistors are often connected in series and in parallel configurations in circuits. Now, how do we determine the difference between series and parallel? So if you have two resistors, for example, and this, remember a resistor does not have polarity. So it has two terminals, but you can connect it either way. There's no positive or negative side. Now, if these two resistors are connected only on one side, they are touching only on one point, and there's no path for the current to divide, then those two resistors are said to be in series. Here we have three resistors. There's a connection between resistor 1 and 2, they are joined at point X. Resistor 2 and 3 are joined at point Y. Then if you apply current on these three resistors, current will flow from A to X, X to Y, and then Y to B. There's no point where the current would split. So these three resistors are said to be in series. Then we move on to parallel resistors. Now the two terminals of the resistor, the left and the right hand side, if they are joined together, then we say these resistors are in parallel. Now here we have three resistors, R1, R2 and R3. All these three resistors on the left hand side, they are all joined together at point A. On the right hand side, they are all joined together at point B. If we have a current that's applied to these three resistors, if the current comes through from point A, it will split into three. Some of the current will go to R1, some of it goes to R2, and the last part goes to R3, and then they join together again at point B. Then when you have series or parallel resistors, you always have to calculate what is the equivalent resistance of the parallel resistors or the series resistors. It gives you the total equivalent resistance of the circuit. Start with resistors in series. So we have three resistors that are connected in series. Since these resistors are connected in series, they will have the same current flowing in all the three resistors. So I1, which is the current flowing in resistor 1, will be equals to I2 flowing in resistor 2 and equals to I3 flowing in resistor 3, which is equals to the total current that flows in the circuit. We also have that the sum of the potential differences across the three resistors must be the same as the potential difference between points A and B. So A and B, if you connect a total voltage there, that will be your total voltage in the circuit from the supply, and it will be equals to the voltage drop in resistor 1, which is equals to AX, plus the voltage drop in resistor 2, which is XY, plus the voltage drop in resistor 3, which is equals to YB. So the sum of the voltage rises, or the sum of the applied voltages, will be equals to the sum of the voltage drops across each of the loads. In Ohm's law, we learned the formula I is equals to V over R. So we can use that same formula to calculate what is the voltage drop across resistor 1. So VAX, which is the voltage drop across resistor 1, will be equals to the current I multiplied by resistor 1. Then the voltage drop across resistor 2 would be VXY equals to I, which is the total current, multiplied by resistor 2. And then lastly, for resistor 3, it would be YB equals to I times R3. And we know that these currents have the same current, which is I. So you can take Y as the subject. We know that the sum of the voltage drops will be equals to the sum of the applied voltage. So the applied voltage here is equals to AB. So VAB is equals to I, which is the total current. Then you sum all those three resistors, R1 plus R2 plus R3. Now the equivalent resistor R will also have the same potential difference across it as VAB, which is your total voltage, because you are using R, which is your equivalent resistance or total resistance of the circuit. So it will also have the same current I. So VAB is equals to I times R. Equating the last two results, then we have that the total resistance R is equals to the sum of the three resistors R1 plus R2 plus R3. Resistors in parallel. So here we have three resistors connected in parallel across A and B. Here we have that the voltage across each resistor has to be the same. The work done in going from A to B is independent of the path. So no matter which resistor you go through, it's still the same work done. V1, which is the voltage across resistor 1, will be equals to the voltage across resistor 2 and also equals to the voltage across resistor 2. And they are all equals to the voltage across A to B. If you have a voltmeter and you connect it across A and B, we're actually measuring the voltages of the three resistors. So resistors in parallel will always have the same voltage. The current is the one that will split into three. Now, dealing with the currents, at point A, the current would split into three distinct currents. We have that the sum of these three currents must add up to the value coming into this point. So I total is equals to I1, which is the current in resistor 1, plus I2, current in resistor 2, plus I3, which is the current in resistor 3. We also have that if you're using Ohm's law, I1 is equals to VAB divided by R1, because VAB is the voltage across resistor 1. So VAB divided by R1 gives you current I1. Then I2 will be equals to VAB divided by R2. I3 will be VAB divided by I3. The equivalent resistor R, we also have the current I going through it. So the current I is our total current. If you calculate the equivalent resistance R, it will have the total current I. Using Ohm's law, I is equals to V over R. And combining the previous equations, we have that VAB divided by R. So VAB is your total voltage divided by R, which is your equivalent resistance, is equals to the sum of the three currents. So I1 VAB divided by R1 plus VAB divided by R2 for I2 and VAB divided by R3 for R3. Or you can use this equation to calculate the equivalent resistance. 1 over R is equals to 1 over R1 plus 1 over R2 plus 1 over R3. The inverse of the equivalent resistance is given by the sum of the inverses of the equivalent resistances. Solving resistor networks. Make a drawing of the resistor network. Determine whether the resistors are in series or in parallel or some combination. Determine what is being asked. Are they asking for the equivalent resistance, the potential difference or voltage drop across a particular resistance? Are they asking you for the current through a particular resistor? Solve the simplest part of the network first. Redraw the network using just calculated effective resistances. Repeat calculating effective resistances until only one effective resistance is left. Given the circuit here with three resistors connected to 18 volts supply, what is the equivalent resistance and what is the current through each resistor? We see that we have two resistors in parallel with with each other, and the effective resistance of these two will be in series with the remaining resistor. So 6 and 3 are in parallel, then the effective resistance or equivalent resistance of these two will be in series with resistor 4 ohms. So step 1, you combine the two resistors that are connected in parallel, then you calculate the effective resistance of the two. So to calculate the effective resistance, we use the inverse formula 1 over R, which is the inverse of the resistance, is equals to 1 over the inverse of the individual resistances. So 1 over R is equals to 1 over 6 plus 1 over 3, which is equals to 1 over 2. Then the inverse of 1 over 2 is equals to 2 ohms. So the effective resistance of the two resistors will be 2 ohms. Then that will be in series with the 4 ohms. So you combine the two resistors that are in series, 2 plus 4 is equals to 6 ohms, which is your total resistance of the circuit. Now, this 6 ohms is your total effective resistance, and it will be applied across this 18 volts. So the voltage across the 6 ohm is equals to 18 volts. Now that we know that the voltage drop across this effective resistance of 6 ohm is equals to 18 volts, what is the current through this effective resistor? It will be given by V divided by R, which is 18 over 6. That's the Ohm's law equation, V over R. So it gives us 3 amperes. So the current through the resistors in the intermediate circuit of step 1 is also 3 amperes. So meaning that the current in resistor 2 that we calculated before is equals to 3 amp as well. So the current in resistor 2 and in resistor 4 will both be 3 amps because they are in series. 4 and 2 are in series. Then you can calculate the voltage drop across the individual resistors. V for 4 ohm, which will be equals to I times R, so 3 amp times 4 ohms is equals to 12 volts. Then the voltage drop across the resistor 2 will be equals to 3 times 2, which is 6 volts. Now, to find the current through the resistors of the parallel section of the initial circuit, we use the fact that both resistors will have the same voltage drop. So resistors 6 and 3 will have the same voltage drop. So I is equals to 6 volts divided by 6 ohms, which is equals to 1 amp. And then I3 will have 6 volts divided by 3 ohms, should be equals to 2 amp. There's a check that can be made to see if the answers for the currents make sense. The power dissipated by each by the battery should be equals to the total power being dissipated by the resistors. The power dissipated by the battery is given by P is equals to IV, where I is the total current. So P is equals to IV, I is equals to 3, and then the supplied voltage is 18, so 3 times 18 gives us 54 watts. The power being dissipated by each of the resistors will be given by I squared R, so P for the 4 ohm will be equals to 3 squared times 4, because the current there is 3, and then the resistor is 4, so it gives us 36 watts. And then for the 3 ohm, the current flowing in the 3 ohm is equals to 2 amp, so 2 squared times 3 gives us 12 watts. And then for the 6 ohm, the current there is 1 ampere. So 1 squared times 6 is equals to 6 watts. The total power will be equals to 54 watts. As an example, here we have two identical light bulbs that are represented by resistors R2 and R3, and these two light bulbs have equal size, so R2 and R3 have the same value. The switch S is initially open. If the switch S is closed, what happens to the brightness of the bulb? So initially the switch S will be open, and then the power is applied only to resistor 2. So it will light up. Then now, if switch S is closed, it means that the two resistors R2 and R3 will now be in parallel. What happens to the brightness of the bulb? Does it increase, does it decrease, or does it stay the same? The power dissipated by resistor 2 is given by P is equal to V squared over R. Where the switch is closed, neither V or R changes. So the brightness does not change because the formula V squared over R, so they will still have this, they will both still have the same voltage if they are connected in parallel. Whether the switch S is open or closed, they will have the same voltage. So V squared divided by R, meaning that we will still have the same voltage across these two light bulbs. So the brightness will not change. Example 2, we have two identical light bulbs that are represented by resistors R2 and R3. R2 is equals to R3. The switch S is initially open, meaning that the current from the source I will be equals to the current that flows in resistor 2. What happens to the current I after the switch is closed? Once you close the switch, it means that you will have resistors 2 and 3 connected in parallel. So what happens to the current? The new current will it be equal to half the current before, or will it still be equal to the same current as before, or will it be equal to 2 times the current before? Now, if you look at this, let's make an example whereby we have two 20 volts supply, and we have resistor 2 and resistor 3 equals to 10 ohms. So it means that at first you will have resistor 2 which is equals to 10 ohms supplied by 20 volts. 20 divided by 10 will be equals to 2 amperes. That's the initial current. Once resistors 2 and 3 are connected in parallel, 10 and 10 in parallel, what is the effective resistance? It would be equals to 5 ohms. So if the new resistance is 5 ohms and you're still supplying 20, 20 divided by 5 would be equals to 4. So the current from 2 amps is now 4 amperes. So what is the answer? C, 2 times the current before. Or you can use the equations shown here. Initially the current was given by E divided by R2. After the switch S is closed, we have to calculate what is the effective resistance. The inverse of the total resistance will be equal to 1 over R2 plus 1 over R3. And we know that R2 and R3 are equal, so we can just use maybe R2. So if R2, it means that the inverse 1 over R is equals to 2 over R. So the total effective resistance R net will be equals to R2 divided by 2. The new current I after will be equals to 2 times the current before, because you used V divided by V times 2 divided by R. So it gives you 2 times the current that was there before the switch was closed. There's another equation we can use when we're dealing with series resistors. Remember, voltage divides in series. So if we have 2 or more resistors in series and we want to calculate the voltage drops across each of these resistors, there's an equation that we use. Vd equals to R2 divided by R1 plus R2 times V. So that gives us the voltage drop across that particular resistor. If you want the voltage drop across resistor 2, we take R2 divided by the sum of the two resistors times the total voltage. It gives us that voltage drop. If you want the voltage drop for resistor 1, we take R1 divided by the sum of the two resistors, R1 plus R2, multiplied by the total voltage. Current divider equation is used for resistors in parallel, because we know that the current would split when resistors are in parallel. So for example, if we have 2 resistors in parallel, R1 and R2, if you want to calculate the current in resistor 1 and the total current is known already, then you take R2 divided by R1 plus R2 times the total current. It gives you the current through resistor 1. If you want to calculate the current through resistor 2, then you take R1 divided by R1 plus R2 times the total current. Here we have 4 resistors. So if you want to use this same equation for 4 resistors, we take Ix. That's the current we are looking for on resistor Rx. So the equation will be RT. RT represents all the other 3 resistors. What is the effective resistance of the 3 resistors? So you will calculate normally 1 over R1 plus 1 over R2 plus 1 over R3. You will get the inverse of that. That will be your RT. Then divided by RT plus Rx, because you are looking for the current on resistor Rx. Then you multiply that by your total current. Then that's the current divider equation. If you're looking for the current in resistor 1, so it means that Rx plus R2 plus R3 will be your effective resistance RT that you need to calculate first.